Hi folks, and welcome to another episode of Open Analysis Live. So today what we're going to do is we're going to look at a malware sample that is packed with a packer that has a whole bunch of anti-debug and anti-VM, anti-analysis tricks in it. This is something that you guys have asked for. I saw in the comments, and I actually had a DM about this as well, something that you guys want us to cover. So today we're digging in. I found a good sample for you guys that has all kinds of stuff, just the kitchen sink of anti-analysis tricks in it, and we'll just walk through that and show you guys how to circumvent these things. So before we get into this, I just want to say that this tutorial is a little bit more advanced than some of the other ones that we've done. Because of the nature of obfuscated code and anti-debugging checks, you basically have to know a little bit about assembly before you can start tackling that sort of stuff. I've tried to slow this down and I've tried to go as step by step as possible, but it wasn't always possible. So if there are any steps in the video that you guys think I skipped over or you missed what was going on, by all means, leave a comment and I'll definitely reply to you guys below. I'll try and explain anything that you might have missed. So here's our sample. I actually grabbed this off of Brad's site, malwaretrafficanalysis.net. I plug that every video. It's a great site if you want to grab malware samples to practice with. I'll actually link it in the description below. And also for all the samples that we work with today, I'll put the links in the description of the video below. I know you guys were asking about that. So here we go. We have our sample, and as you can see in hybrid analysis, if we go down to the actual process list here, the sample was run, but nothing else really happened. There's no network traffic, there's no other processes spawned, there's no files dropped. So this might be a good indication that this sample detected that it was in a sandbox and it didn't run. So that's why I selected this. I thought it would be a good one because it didn't even run in hybrid analysis, which is pretty decent sandbox in terms of hiding itself. It usually bypasses most sandbox detection, but in this case it did not. So what we'll do is we'll copy the sample down and then load it up in IDA, and we'll load it up in a VM and just kind of run it and take a look. So today I'm going to be using two VMs like I usually do. We have one that's the victim, and that's what we're looking at here. It's just a Windows XP VM. And then the other one is my analysis box. So this is where I have IDA installed and all my tools. And so the way it's going to work is I'm going to have IDA here on this VM, and I'll be debugging on the other VM so that if anything goes wrong, it's not going to affect my IDA license. And I can just take a snapshot of the other VM and revert it if I need to. So let's take a look at that victim VM here. Here's the sample that I grabbed. I called it anti-debug sample, just, so we can keep it clear of what it is. And the first thing I'm going to do is just kind of load it up in PE Studio and see what it is. So the reason why I did this is sometimes you can get lucky. Maybe it's a common known packer that we have an unpacker script for or something like that. So in this case, it's kind of interesting. If we go down and kind of look at the properties of the file here, you can see this signature Bobsoft mini Delphi, which kind of looks familiar to me. I think I've seen that before. I'm not quite sure where. Let's see if we can get any other information about it. Oh, okay, so it looks like this is actually AutoIT, which is like an installer where you can have a bunch of scripts and then you can package your binary and the scripts and everything into one exe, and then it's kind of like a one-click installer. I've definitely seen malware packed with this stuff before, and up until so if we look at the version here, so up until like version 3.2, I think 3.2 something, there was a tool that would actually automatically extract the installer script in the binary for you. It was pretty awesome. Unfortunately, it looks like these developers knew that, so they're using a newer version, 3.314. I don't think there's a tool for it, so we're gonna have to actually deal with a debugger. But always worthwhile to just kind of check this stuff out just to see if maybe we could have shortcut this. So it looks like we're not gonna be able to do that. What I like to do as well, just in case we get lucky, is run Process Explorer, take a look at what's going on, and actually just run the sample. So here we can see it's running at the bottom down here. And so it looks like it's actually maybe doing some unpacking. It has, there's some activity going on here. I'm not hopeful because if hybrid analysis wasn't able to trick it, I really doubt that my VMware VM that I haven't hardened at all is going to be able to trick it. But it's always worth trying, always worth giving it a shot. So it's running, and magic of time lapse. It just exited, nothing else happened, nothing interesting. So it looks like we're probably gonna have to open this thing in a debugger. So here I've already loaded the file in IDA, and so now we just have to set up the remote debugger. So we're gonna do Windows Remote Debugger. On the other VM, we have to start our Windows Remote Debugger. So I just started the remote debugger. It's running on IP 131. Just remember that. Let's go to our debugger process options and hostname 131.131. Okay, cool. And like I always do, I like to put a breakpoint on the start and then just start running it basically. Okay, so now that we've started our debugging session, we can put some breakpoints on a few APIs that might be used to detect whether it's being debugged or whether there's a VM present. What I'm going to do is we'll take a second here to look at some of those interesting APIs that we might want to hook. I realize I say hook APIs a lot. I talk about hooking APIs in a debugging session, and I just want to clarify for anyone who's wondering, when I use the word hooking, really what I mean is I just put a breakpoint on the API, on the entry point of the API, and then I take a look at the data that's passed to it. So I use the term hooking because it's kind of the same concept, but it's not exactly hooking. So just keep that in mind. I think I had a comment about that, so I just want to clarify. All right, let's talk about APIs that we can hook that might tell us what's going on, what is happening with this binary. What I'd like to do is I'd like to pull up a few documents on anti-debugging techniques, and I'll link these in the description below so you can take a closer look at them, and I'll sort of walk through this quickly with you guys. So here I have open the ultimate anti-debugging reference. It's fantastic, and like I said, I'll link it in the description below the video. And I also have The Art of Unpacking from a Black Hat talk. Both of these they have a lot of overlapping stuff, but they're both excellent references if you want to find out what all the tricks are for anti-debugging. Basically, if you're trying to unpack something that has a lot of anti-debugging, the methodology it's very simple. There's no real tricks. I mean, I can show you, I am going to show you a few shortcuts, but in terms of getting started, there's no real trick to it. Really what you do is you set breakpoints on all of the APIs that you think might be being used to detect a debug session, and then you run the binary in the debugger and you see if any of those APIs are hit. And if they are, then you check out where they're being used in the code, and maybe you can see what sort of tricks are being used. So it really is not a fast process. Really, if you want to do this stuff fast, if you're doing this professionally, there's two tricks to it. One is have a virtual environment that is scrubbed completely clean. So I can talk about this in another video about how to harden a VM, but that's step number one. And step number two is don't use a debugger, use a hooking engine that is hard to detect. So basically what we're talking about is build a good sandbox. That's that's how you unpack quickly. If you have to do this in a professional environment. But today we want to talk about the basics. We want to talk about the foundation of how you do this, so that you have the concepts behind it when you go to implement this at a larger scale. So we're going to do it all manually, and we'll talk about what these different anti-debugging, anti-analysis tricks are. So let's start with the ultimate anti-debugging reference, and what we'll do is we'll scroll down. There's this nice section called APIs. So these are a bunch of APIs that we might want to hook, and what I'm going to do is I'm just going to start adding breakpoints to them in our debug session. So we have check remote debugger present, create tool help snapshot, there's is debugger present, anti-query information process. There's tons and tons of these APIs. So if you had to do this from scratch and you were really lost, you would just basically add breakpoints on all of those APIs, and you would run the binary and check and see what's going on. So that's what we're going to do today. We're gonna try this method out here. So let's look for check remote debugger present. Here's how we set our breakpoints. We go over to kernel 32, Control F, check remote debugger present. And we add a breakpoint here. I'm going to do Control F, is debugger present. So we're going to add a breakpoint here. What were some of the other ones that they listed? Create tool help 32 snapshot. So the debugger ones are pretty self-explanatory, but let's talk about create tool help snapshot. Tool help 32 snapshot. So basically what that does is it returns a pointer that you can use to list all of the processes that are running. So anytime you see create tool help 32 snapshot, really what you have to think about is get process list. That's kind of, it's analogous to that basically. So we definitely want to put a breakpoint on that, because if they want to do any searching to see if any processes are running that are related to a VM, they're definitely going to probably use that API. So create tool help 32 snapshot, add a breakpoint, and let's see what else they have. So also anti-query information process. So the way anti-query information process works is you have a call that can be used to get information about a process depending on the information class that you send it. So there's a whole list of process information classes that you could check for, and have this open over here. These aren't formally documented, a lot of them, but the ones that we're pretty much interested in is if we look for debug. So there's, you can check for debug port, you can check for debug handle, and you can check for debug flags. I think there's a bunch of other stuff. So basically the way this works is if you call NT-query information process and you pass it like 07 or 1E or 1F, then the result can be used to determine whether there's a debugger present. So we definitely want to hook that thing. And that's in nt-dll.dll. NT-query information process. So let's add a breakpoint here. Okay, so that's probably enough to get started at least. I'll jump back to our instruction pointer here at the beginning, and let's set up our IDE instance so that it looks a little bit nicer. Let's give ourselves an advanced toolbar, and that just gives us the extra buttons up there that I like to click on, and we'll show a bit more of our stack here. I want to see more of the registers. Okay, so now what we want to do is actually just run this and see if we hit any of the breakpoints that we started. So now we're running, and what I'm going to do is I'm going to pop over to our VM here just to see how we're doing. So it's running, looks like it's doing its thing here, probably unpacking something because we can see a little bit of CPU usage. So let's pop back over to our debugger and see how we're doing. And it's still running. It might take a minute with the debugger attached and stuff. If we'll see if we'll hit one of these hooks that we've set or one of these breakpoints that we've set. So I'm pretty sure that we will. I have confidence, seeing as I picked this sample. So I'm pretty sure we'll hit one of those breakpoints. No use taking up your time. Let's just use a magic time lapse. Okay, actually that was amazing. As soon as I snapped my fingers, it it actually hit on create tool help snapshot. It looks like that they're using this API. So what we can do is our old trick, which is run until we return. So we'll return back into the code. Here we go. Here's our actual code that was running. So this looks like a little segment of code. It doesn't look super well defined because maybe there's some obfuscation. Hint, hint. Yeah, there's definitely a lot of obfuscation in this. So let's take a look in this code here and see if we can see the call that was used to call into that API create tool help, just to see how that's working. Really what I want to look for is to see whether the API was dynamically resolved or whether it's one of the imports. I don't think it's one of the imports. I didn't show you guys that, but I did check them off camera. So the way to do this is here's our instruction pointer here, and that's where we return to. So probably the code above it is where they called the function. So let's just move over there and press C to turn it into code. So here we can see a call out to ESI 0 with an offset. Let's jump in there and let's see if we can do a DDD to turn this into a D word. Yeah, and indeed this is a pointer to create tool help snapshot. So it looks like what they've done is they've dynamically resolved some APIs. So you can see this in the debug section. And if we go back, they're calling it by reference basically. So that's a good indication that this is a dynamically resolved API. And what I like to do, this is a little trick, is let's open this in a new window so we can play around with it a little bit, is anytime you see a dynamically resolved API like this, there's a good chance that there's probably other dynamically resolved APIs around it. So I'll just go down here and I'll press DDD again to turn this into a D word. And yeah, so we have some other dynamically resolved APIs as well. Oh, it looks like the section starts here. So let's see if we can turn these all into, yeah, they're all APIs. So what we found here, just by hooking that possible anti-debugging API, an API that could be used to list the processes, we've been able to hop back into the unpacked or some unpacked section of code with a bunch of dynamically resolved APIs. So this is like a first good step, because with these APIs, we might be able to get an idea of what other anti-debug tricks there are. And then what I'll do is I'll walk you through how to determine what these anti-debug tricks are and how to circumvent them. But first things first, let's just take a look at the APIs that they've dynamically resolved. Okay, so now we have all of our APIs labeled here. So we can see what APIs they want to use in this little bit of code that they've unpacked. So we can see our create tool help snapshot, some read process memory stuff, write process memory. So maybe they're going to do some process injection. And I think I saw a create process in here. Yeah, create process. So probably pretty likely that they're doing some injection. So I can tell that by the fact that they're creating a process. They have a get thread context, which usually means they're trying to figure out how the process is laid out after they've created it. They have a write process memory, which is, all of these APIs can be used for process injection. So I'm thinking that's probably what we're going to look at. That's probably going to be the final stage here. We can also see some other anti-analysis stuff here. So we have that anti-query information process. So we know that they're definitely going to use that at some point. Those look like two good APIs to look at to see if there's any anti-analysis stuff related to them. Going back to the code that we were just hopped into here, we can see that we've just returned from create tool help snapshot. So we actually have in one of our arguments that we passed, we'll have a pointer to that list of processes. And so why don't we do a couple steps here to see if we can tell what they're actually doing with the results of that process list. So what I'm going to do is I'm going to step through some assembly here. So it looks like they move EAX into EBX and then they're checking it for -1. So they're just checking the return value to make sure that it returned properly. And I guess if it didn't return properly, they're going to jump somewhere else. But it did. Okay, so we're just going to continue on here, keep stepping through. I don't see anything super interesting just yet. We can see there's a call out here to process 32 first W, which gets the first process in the create tool help list pointer of processes. So it looks like they are going to actually get process names. Probably, most likely, that's what they're going to do. So let's skip over this. We don't really need to jump into the API because we know what it does. And actually, we should probably just 32 first fist first. Should probably just put a label on there just so we remember what it is, and then we'll keep going here. So this is, as you guys can see here, this is pretty obfuscated. It looks like what they've done is they've taken functions and they've split them apart and used jump statements to connect different sections in the function together. And if we look up here, it looks like they're using this E4 as like a separator in between the functions. So you can see this like E4 is here, and so E4, 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 and then there's a bunch of what looks like maybe code and then E4. So I think if we like go to here and we just press code, yeah, we can turn these into blocks of code. So here's a bunch of E4s here. So let's turn that into code. So you guys can kind of see the setup now. So they basically have taken functions, they've split them apart, they've used jump statements to connect the different blocks, and then in between the blocks, there's these like E4 obfuscated garbage that we're not going to care about. So what I think I'm going to do is I think I'm going to, through the magic of video, I'm going to turn all of these sections here in between the E4s. I'm going to turn them all into code sections, and I'm going to add a few labels to them, and then I'll come back and with it all labeled up nice, and we'll see if we can't take a look at this so that it makes a little bit more sense. Okay, so you can see I've been busy labeling here through the magic of video. After that snap, I went through and I walked through and added labels to a bunch of these functions, or I guess they're not functions really, they're sections that are being called into because the functions have been kind of destroyed by this obfuscation, like I was describing before. So I've added a couple of labels just to try and make this a little bit faster. In order to do that, I had to step through the code, and it takes quite a bit of time, and I don't think there's a lot of value in showing that in just having a giant video where I'm stepping through code and then labeling stuff. So what I'm going to do is I'm going to go over a little bit more of what the anti-debug tricks actually are. Now that some of the stuff is labeled, it'll be easier to see. So here in this variable here, we have what looks like a process name called system process that we probably got from that create tool help list, process list. And it says system process, but if you use the create tool help function in order to get what is basically a list of processes or a pointer that you can walk and thus get the list of processes, The system process has this silly designation here. So that's just the name. You'll see some of the other names are going to be called other stuff like, like LSAS and whatever. So like I was saying, I put a label here. This is actually getting the string length of this variable that's passed in, and it's going to store it in EAX. So let's skip over this. We can say EAX has hex 10, so 16 bytes. So that matches, right? System process with the 2 brackets in the space, 16 bytes. So it's comparing the length of the string in EAX to 40 hex, which is 64. And so it's seeing if the process name length is 64 bytes long. And if it is, it skips this jump and we go down here and we call into exit process. So why would they be doing that? What are they looking for there? Well, this is actually kind of a silly mistake, I think, on the part of the developer. So what they're doing is they're checking for any process where the name of the process is exactly 64 characters long. And if any of those exist in the process list, it actually kills the unpacker, so it doesn't unpack. Now, I think what they're trying to do there is they're trying to see if any of the process names have a SHA-256 sum as their name. So a lot of times if you download a sample from VirusTotal, the sample name will be 64 characters long, and that'll be the SHA-256 sum of the file. So I think what they're doing is they're checking to see, are there any processes that are being run with SHA-256 file names. Now, that's a good trick. I've seen this before. A lot of sandboxes will run a sample, will rename it with the SHA-256 sum as its file name just to track it properly. So this is kind of a clever trick. But one thing I think that's kind of weird about it is they're checking for 64 bytes exactly, and they're not accounting for .exe, right? The appended file type on the end of it. So I guess maybe some sandboxes run files. They have a way to run the files without the file handler on the end of it. That you can definitely do that if you're starting stuff via like shell execute and commands like that. You don't need that file handler on the end of it. So I think to make this a little bit better, they should be checking for either 64 bytes or 68 bytes, right? So either just the file name, a SHA-256 sum as the file name, or a SHA-256 sum.exe on the end of it, right? 4 extra bytes. So I think that would make this a better check. I think this might have been a bit of an oversight on the developer's part. So obviously none of our processes we're not using SHA-256 as the file name, so we don't really have to care about this check. So let's continue on here. We'll keep jumping through the code. So now what they do is they turn the process name into lowercase. Oops. Let's go back here and we'll set a breakpoint here and a breakpoint, and we'll just run until we get there. Because again, we don't have to step through all the code to turn it into lowercase. We know that we're turning it into lowercase because I already walked through and labeled that code. So now that they have it in lowercase, what are they going to do with it? I don't know. We have a bunch more jump statements, some more garbage. And it looks like they're copying it into a buffer. Okay, great. So they turn it into lowercase and then they store it into a buffer. So I think what they're probably doing is they're probably going to do this. Yeah, here we go. So the next API call we have is process 32 next, which means get the next process in the process list. So I think it's safe to say that pretty much all this function is doing is checking if the process name is 64 bytes long. If it is, it terminates the unpacker. If it's not, it stores it, it turns it into lowercase and then stores it in a process list. I mean, okay, cool. They're probably going to use that process list later on in another function. So why don't we run until we return from this? And what that's going to do is that's going to give us a, sorry, let me turn this into code here. So what that's going to do is that's going to give us a run back until this process was called. So you can see I've added a label here, get process list, check 64 length, because I've already walked through this. So we can see that's one of the checks that they've done. And you can see what they're doing here is they're actually testing the return value, which is in EAX. So this could be a flag, maybe that they're testing. Kind of interesting that they would be doing it that way to see whether any of this stuff failed. So I mean, it didn't, so we don't really care. And then the next check is they check the name of the malware sample. So let's look at that check. We'll step into that and we'll talk a little bit about how that check works. All right, so let's jump into this function here and see how they're checking the sample name. So we can see that there's a bunch of setup stuff here that we don't really care about. And then we started to see this weird stuff where I've actually just turned these into letters so you can see, but normally they look like this. So they just look like hex characters. And we can see there's like a push pop into EX, push, and then EX into, ECX into EX. So let's see what's going on here. And then it looks like they're moving AX, so the character, so only 1 byte, into this variable here. So let's skip past that and I'll just show you. So in the variable, they've put an S. And it looks like they do this a bunch of times. So let's skip through a few of them and now let's look at it. So it looks like SAM. So I think what they're doing here, it looks like it's a little bit hard to see because this is split out with a bunch of jumps. But it looks like this is just a standard stack string build. So if you're not familiar with what stack strings are, it's basically a way to obfuscate, it's a simple way to obfuscate strings. So instead of having a constant string in your file, so a constant set of bytes, what you do is you have a bunch of code like this, which pushes 1 byte at a time onto the stack, and then you use the reference to the beginning of that string in the stack as the string. So it's a way that you basically dynamically build strings so that they don't exist if somebody runs strings on your binary. And what this means is that if we want to see what these stack strings are, we're going to have to click through a whole bunch of code where they build the stack strings, and it just it takes forever, right? Because they're building the strings 1 byte at a time. It's super frustrating. So and then once they've built them, you can see like we'll move over. I'll jump to this in a new window so we can see. That's our stack, right? So we can see there's like sandbox. Maybe that's going to say sandbox. What else do they have on here? They have sample. Do they have anything else? No, nothing else, I don't think. So these are basically stack strings. So so this stack string would be I think this is going to be sandbox. This one would be sample. So given that and the fact that I already know what this function is doing, which is it's comparing the process names against these strings. So why don't we let it run until it exits and then, or till it returns, sorry, and then we'll see what the and we'll get to see what the stack strings all are, because we can just, of course, look at the stack. So I'm going to keep this window open as a reference because we know that the stack strings will be built here. And what I'm going to do is I'm going to run until we return from this function. Now, you might be saying, well, you don't really know what it's doing. You don't know how it's all working. But remember that when they return from these checks, they return a flag in EAX, and then that flag is actually being used to determine whether the unpacking should continue. So what we can do is we can do this pretty safe, right? We can just run until we return, and then we just check the flag to see whether we've been caught or not. And then we can also check the stack string flags, the stack strings, just to see whether any of our processes match up with the stack strings. So let's do that. We'll just run until So now that we've returned, we can see that there actually is one of the flags is set here. It's actually purple because as I was waiting for it to return, I just automatically set it to 0 so that it wouldn't trigger the unpacker to stop unpacking. But I put it back to 1 so that you guys can see that the flag was actually set. So one of the strings was detected. So why don't we take a look at those strings and see what they were and why something was detected. So remember, this window here is where I have a pointer to the stack, and this is where the stack strings were. So if I just come over here and I press A to turn these into strings, we can see what the strings actually are. Virus, self dot something, sandbox, I think that's it. So what they were doing was looping through all the process names that they collected and checking to see whether any of these strings existed in the process names. So they're looking for not just our sample, but also some other processes that might be running. So remember, we called our sample up here, we called it anti-debug_sample. So this actually caught our sample, and this is one of the reasons why our sample wasn't unpacked. So we're gonna have to change the name of our sample, or we're gonna have to change this anti-debug trick return value. So we can change the EAX to 0 to make it look like this string wasn't found. So they also check for virus, self.something, I'm not sure what that's for, sandbox, and malware. So let's come back over here. Like I said, I just changed the flag to 0 so that it looks like none of the strings are found. But I'm also going to change the sample name after this debug session so that it actually runs. So here we go. It looks like we're testing EAX, so we test that flag. And because I changed it, we're doing the jump. So the next thing they're going to do is check for some AV strings. So they're going to check the process list for some AV strings, I guess for avast. And that I'm actually not going to show you guys because it's kind of boring and doesn't really relate to us because we don't have avast running. That's not really, so this is like an anti-AV check, not an anti-debugging check. I would assume that in your VMs that you're running malware, you don't have AV, so you don't have to worry about this. So I'm just going to skip over it. And we'll keep going here. So there's another, we'll have to keep going. Okay, so now they're going to check more strings, and they're going to check for debug stuff. So why don't we take a look at how they do that? So we'll hop into this check here. So again, there's a whole bunch of it's hard to read this code, which is why I had to add these labels, because everything is really split apart. So it's difficult to sort of to see the whole picture. But what I like to do is I like to kind of go until we either see them building some stack strings, or until we see them calling some APIs. So here again, remember, see these single byte pushes. Let's see if we can use R to turn these into characters. Yeah, it looks like, again, they're building stack strings once again. So stack strings, yeah, I think so. So why don't we, again, step through this stuff pretty quickly. I think they're probably building a lot of stack strings if I remember correctly. So why don't we use that trick again where we run until we return from this debug check. Again, we're not too worried about it exiting the unpacking just yet, because they always check that return flag from the debug check first before they do anything. So we have a chance to change that if we need to. And also when they return from this function, because we have our window open to the stack here, we can check and see what stack strings were actually built. So again, this is a quick trick if you want to see what's being done. Now, if you're doing this, you might find a situation where you run until return and then the process exits, right? Because somewhere inside that function, they were actually checking something that caused the program to exit. And if that's the case, it's not a big deal. All you know is that next time you can't skip over that function. You have to run through it and find out where they're exiting. Again, it's like kind of a trial and error thing here, and it's a little bit slow going. And I don't want to make a 4-hour-long video, so I'm kind of skipping over a few of these things. But again, there's no magic. I'm not skipping over any tricks. All you're doing is basically reading the assembly to find out what the function is doing and then labeling it. That's basically it. So let's run until we return here. Oh, what happened here? Oh, interesting. So actually, as I was describing, what I was just saying actually happened. So there was actually a check in that function which determined if they found one of those strings, maybe they called into exit process. I'd actually previously put a breakpoint on exit process, which I didn't show you guys, but that's just one of the tricks that I guess I should have mentioned, where you definitely want to break on exit process so that you can see what went wrong if something went wrong. And in this case, what I'd like to do is I'd like to take a look at the stack strings and see, oh yeah, okay, I think I see what's going on here. So we were checking process. So we're checking the process names against some more strings, which I'd called debug strings, I guess, when I was labeling that function. But it looks like it was probably more than debug strings. So let's go over to our stack here and let's turn these into strings. Yeah, you can see, can you guys see what's going on here? Let's just turn them all in so we can see. Yeah, there's more up here. Is there any other ones? No, that's it. So it's checking for these processes. Process Explorer 64, Procmon 64, Procmon, OALabs, Process Explorer, and WinDebug. So let's pop over to our VM here, and we can see we're actually running Process Explorer. So that's probably the issue here. And here's a trick that you guys can do that I like to do. I actually knew that this was going to happen, so I called this Process Explorer. But I actually always rename Process Explorer for this exact reason. So let's call this God mode, godmode.exe. So I like to just rename it so that if malware is actually checking for it, it won't be found. So now that it's called God mode, not Process Explorer, let's go back and start debugging again and see if we bypass that check. Come back here. We're going to stop. Actually, sorry. Let's go back to check debug process names, and we'll add a breakpoint here so that we can find that easily next time when we run this sample. So let's stop our debugging session. Let's start it again. We're going to run into start. We'll just double check that this is running here. So God mode is running, auto is running. Oh, that's right. I renamed the sample to auto.exe instead of what was it, debug example or something, because anti-debug sample, because I wanted to bypass that sample check where they were checking the process name for the word sample. So let's pop back over to WinHacker here. So we stopped on create tool help 32 snapshot, but remember we set a breakpoint on that function that we failed on. So let's just run until we hit that function. There we go. So here's the magic of this is when you can really see that having VMs and a bunch of being able to add breakpoints and revert to where you were before. If you make a mistake, it's super helpful. So let's run this and see if our changing Process Explorer, the name of Process Explorer to God mode, see if that changed the result of this debug check. So let's jump over it, and there we go. So we didn't end up exiting. It looks like that name change helped. Let's delete the breakpoint, and we'll continue on here. Let's go down. So our next one is a debug check with query info process. Remember I showed you guys at the beginning of the tutorial, this is a way to query information about the process, and based on the process info key that's passed into the function, you'll be able to query different types of information. And if we just pull up that browser for a minute that I had open, we can see that the information that you might want to query would be about, like, the debug port is 07, the debug object handle is 1E, debug flags is 1F. So if any of these keys are passed into query information process, then we can be reasonably assured that they're actually checking to see whether one of these debugger tells is present on the host. So we'll actually step into this and show you guys how it works. We'll come down here. Just again, the setup with the jumps, kind of hard to follow, but trust me, we're not doing anything interesting yet. We're just doing the setup. And then we'll come down to here, which is a call. So we'll just hover over here. That's our NT query information process. So let's label that. Okay. And then let's see what's being passed into this API. So the arguments on the stack here. The first one is, actually, let's pull it up in the browser just so that you guys, to refresh your memory here. So the first argument is the process handle, and then the second one is the information class. So let's take a look here. So the first thing on the stack is a process handle, and all F's means -1, and a process handle of -1 means your own process. So we're saying query this process, and we're passing it the key 1F, which I think was one of the debug tells. So what is 1F? 1F is process debug flags. So we're checking if there's any process debug flags present. And so let's go back to our assembly here. So let's call that API and see. Oh, shoot. I jumped into it. Let's just run until we return from it. Okay, so to understand how this debug trick works, we have to actually look at the documentation for it a little bit. It's a little bit less intuitive than you might think. So let's hop over to our browser here, and I've actually pulled this up. So the way that this works is the process debug flags class returns the inverse value of the debug flags. So if the return is 0, it means that there's a debugger present. And if it's another number that's not 0, then it means that there's no debugger. So it's a little bit counterintuitive. It's the opposite of what you might think. So if we come back here, that's why they're actually checking. So EDI is 0 here. That's why they're checking to see if that return value is 0. And if it is, then they jump. So what we'd like to do is we'd like to just tell it not to jump, basically. So there's the jump 0. So we're going to tell it don't jump 0. So just set our IP here. So what I've done there is I've just told it like don't take that jump. So it would have taken the jump because the return flags were 0, which is the inverse of what they really are, meaning that there is a debugger there. So it was trying to take that jump, and I just told it not to. So let's continue on and see what else they have in store for us. Again, there's more setup stuff. And then there's another call, and it's again to NT-query information process. So it looks like they're checking more than one thing through NT-query information process. Again, let's NT-query information process. Just label it so that we know what's going on. So let's take a look at our stack here. The top of our stack again is -1 or all Fs, which means this process. So we're querying the process that's actually running, and we're sending it 1E. So remember, if we go back to our diagrams here, 1E is right here is process debug object handle. So we're checking for the debug object handle, and let's take a look here. We'll come back over to our anti-debugging tricks, and we'll see if they can tell us a little bit about what that's doing. So what they're doing here is they're actually checking to see whether that returns a value. So if it's returning something that's not 0, basically. So the way that they're doing it is they call out to NT-query information process. They take the passed argument off the stack into EAX. They test it. They jump if there's a value in EAX. Basically, they jump if it's not 0. So we'll have to keep that in mind when we see the return here. So let's jump over this API call. They're testing EAX, so they're just testing the return to see whether it actually worked. So remember, EAX doesn't actually have this debug object in it. EAX is the return code from the API call. So it just tells you whether the API call returned successfully or not. We can see here that it did, return successfully. So here. Whoops. Oh, I see what they're doing. Okay, so they're actually just checking to see whether it returned at all. And then they're telling us that, yeah, there's that the return tells us that there's a debugger present. I missed that, I guess, on the first pass, but that's what they're doing. So let's return back, and we can see that our flag here is set to 1. So remember, we've returned from our call here, and the flag is set to 1, which means that there is a debugger present. So let's change that to 0. And make this okay. So now at this point, there's other debugger, lots of other anti-debug tricks, but I think that this is enough for you guys to get an idea of how to do this. You basically use those documents that I'm linking in the description below that have all the different APIs that could be used to detect whether there's a debugger present. You load it up in your debugger, you load the malware in your debugger, you add breakpoints on all those APIs, you run the malware. Anytime you hit the API, you hop back into the malware code and you check and see how that API is being used. So in this case, they're checking return values from the APIs, and they're using that to determine whether there's a debugger present, whether there's a process explorer present, or whether there's any process name with 64 bytes long. They're checking whether process explorer and sample and sandbox are strings that exist in any of the process names. So these are all, I'm just going through high level what we've already determined about this program. So this is how you do it. You can see here that's very slow. And I think what I'd like to do is I'd like to leave some of these other debug tricks up to you guys to test out yourselves. So I will provide links to the samples and everything below so that you guys can take a look at this yourself. You can use the exact same process that I'm using here. And what I'd like to do is I'd like to show you guys a trick to basically circumvent all this stuff. So let's stop our debugging session here, and we'll hop over to our victim VM here. We don't need this remote debugging anymore. And let's change this name to auto.exe. And we've already changed the Process Explorer name. So what we're going to do is we're going to go back. We're going to get old school here.
What we're going to do right here is go back. How far you going back? Way back. As we go a little something like this.
So we know that this packer here is checking all the running processes for a bunch of strings that it has. And so we can see here in Process Explorer that none of the strings that they were checking for exist now in the process names because we've changed them all. So what we can do is we can run it without a debugger, go super old school, and see whether it'll work now. So let's double click to run it. We can see it's running here. It's doing its thing. And we'll see whether we've already bypassed all the anti-debugging checks by just simply running it. Oh, yeah, look at that. So it started, I'm going to pause this. So it started if you guys caught that really quickly, it started a version of itself. So remember I said earlier when I was looking at those API calls, it looked like it was going to do some process injection. So what we saw here was it started itself. Again, it ran itself, and then the original program exited, and the version that it started is still running. So I'm going to show you guys a trick here. I'm pretty sure that this is process injection. It looks like we've bypassed all the anti-debugging checks. So all we have to do now is dump this process. I'm going to show you, just for fun, super old school way to do this. Those of you guys who've been around for a while remember this. Remember LordPE? I'll put a link to this tool in the description below. Again, I don't think anyone uses this anymore, but I think it's hilarious just to let you guys know a little bit of history, reverse engineering history. So LordPE a while ago, a long time ago, was like the process dumping tool, and you'll see why in a second here. So we can just select the process here, and then we can just do a full dump, basically. Yeah, I can't find the original PE header, that's fine. Let's save it here as dump.exe on the desktop. Let's save it. Dumping is done. And what we'll do is we'll copy that file over to our IDA instance, our VM with the IDA instance running, and we'll take a look at it and see whether it's actually unpacked. So we open up dump.exe in IDA on our virtual machine that we're running IDA on, and let's take a look at the strings first to see if we got what we needed. Oh yeah, so it looks like, yeah, here's a bunch of Loki strings. So I knew that the sample was going to be Loki because when I found it on Malware Traffic Analysis, Brad had already identified it as Loki based on the network traffic. So the fact that I see the Loki strings here, you can see here's all their credential stealing paths and stuff like that. So we can see that we've actually successfully unpacked it. So this is kind of like the funny conclusion to this tutorial. So I hope that by showing you guys manually how to go through and circumvent anti-debugger and anti-VM checks, you can see the process that you would need to use if you need to do this. But the conclusion hopefully points you guys in the right direction, which is that usually just by a couple tweaks, just changing the file names so that they're not something common, make sure any of the analysis tools that you're using don't use common names, make sure your VM is relatively clean. You can probably just run it and dump it out with it. You know, you can probably circumvent all these debugger checks, all of these anti-analysis checks. So hopefully you guys found that interesting. If you have any feedback, questions, comments, you want to see us explain something a little bit further, please make sure to leave your comments below. We're definitely paying attention, or you can DM me or Sean on Twitter. Our links are in the description below as well. And also, I would totally encourage you guys to make sure to subscribe and turn on the little notification button. We're doing one tutorial a week, so you won't miss one if you subscribe and spread the word. So until next time, keep exposing the mechanics behind the malware and stay curious.